Okay, this is the priority scheduling algorithm, but this time implemented in a preemptive environment. So preemptive meaning, remember, it can be preempted. So there's a clock interval that will ensure that after a certain amount of milliseconds quanta, we will interrupt the specific process. But this specific implementation also says that even if you have a high priority, as you get CPU time, the next time you run, your priority automatically decreases, meaning you get into a lower band of priority. So let's have a look. Initially, we have in this example 4 processes, again A, B, C, and D, different priorities. If you look at this, because we assume that 0 is the highest priority, B currently have the highest priority, and it potentially will run for 12 milliseconds. So let's have a look and see how this will work. Firstly, B will start running. It's currently running in priority 1. You guys see that? And it will run for a maximum of 5 milliseconds. After 5 milliseconds, it gets interrupted. So let's subtract the 5 milliseconds here, which means that we have 7 milliseconds left. As soon as it's finished running, the scheduler automatically lowers the priority of the process, which in this case goes from priority number 1 into priority 2. The scheduler then again re-evaluates the table and again evaluates which one of these processes has the highest priority. In this case, it is B. So again, B will run, but this time with a priority level of 2, and again for only 5 milliseconds. Of course, when it's finished running, for our case, we subtract this, so it's 2 milliseconds left, and it decreases the priority, which in this case now means priority 3. Now, again, the scheduler evaluates priority levels, and the scheduler can choose either A or B. Okay, it doesn't really matter which one, depending on how you implement this is really up to the implementer. In this case, let's assume the scheduler selects A, just for a little bit of a difference. It currently runs in priority level 3, again for 5 milliseconds. The amount of potential CPU or burst time left for this process is now 6, and it automatically increases the priority. All right, now the scheduler again looks at the table. Which of these processes now has the highest priority? In this case, it's B. So again, B will run with a priority level of 3, but this time only for 2 milliseconds. Right, it runs for 2 milliseconds and it blocks. Let's assume it blocks. So it gets removed at the table. There we go, it's not in the ready state at this stage. Right, next, the scheduler again looks at the processes that's left. It's A, C, and D. It can choose either A or C, it doesn't really matter. Let's assume it runs A. It runs in the priority level 4, of course, and it will only run for 5 milliseconds. So there's 1 second left, and the next time it will have to run with a priority 5. It basically got interrupted. The scheduler again looks at the table. The scheduler says, okay, the next guy that will run is, of course, process C. It runs in a priority 4, and it will run for 5 milliseconds. So 5, 6, 7, 8. So there's 3 left here with the priority 5. And now the scheduler can choose any one of these. Doesn't really matter. Let's assume it again runs A, because that's the first one it basically searched for. And it says, I will run in priority 5, but it will only run for 1 milliseconds, and it blocks. Now, scheduler again selects. Let's assume it selects C. It runs with a priority 5, again only for 3 milliseconds, and it blocks. Thank you. Next time, D runs. Now have a look at this. D runs for 5 milliseconds with a priority of 5. What happens now? Well, there's 10 left, and it decreased its priority. So the next time, D will again run, this time with priority 6, Also only for 5 milliseconds. All right, that means we've got 5 left, and this time with a priority 7, and the last time it will run 7 RD with a priority level of 7 for 5 milliseconds, and then only does it block. Okay, so the challenge here is that hopefully you've seen that as the processes run, they initially get assigned a specific priority level, and as they get CPU time, the priority levels go down. Operating systems may have the ability to increase priority levels again, given certain scenarios. For instance, if you have an application that becomes interactive, meaning becomes the active window inside your operating system, potentially you want to boost its priority level so that it gets a little bit more CPU time. It may also be possible on a server environment that certain processes that are doing mission critical information can automatically get boosted by the operating system. Okay, but that's the basic idea behind it. So it's effectively a system where priorities decrease. Now, hopefully you've seen that there are a bit of issues that happens when priorities are the same. How is that handled? The example here was just pure, simple, well, we randomly selected one, or the first one. The next examples that we will look at, we will discuss that in a little bit more detail.